Still only 7 are present. Out of 23, only 7 has come. Okay, then we shall start this class. So yesterday we were discussing about electric flux. So electric flux we have already discussed, that is given by the dot product of electric intensity and area vector. So electric flux is a scalar quantity. So it is given EA cos theta, where theta is what? Theta is angle between electric field intensity and area vector. If angle is given with the surface, then this phi will be EA sine alpha, we have seen, where alpha is angle made by electric field intensity with the surface. So in the formula EA cos theta, theta is angle between area vector and electric field intensity. Whereas in the formula EA sin theta, sin alpha, alpha is angle made by the. So if this is the surface and electric field intensity is this way, then with the surface, whatever angle, this is alpha, whereas this is the area vector, this is the electric field intensity, this angle is theta. So either theta is given or alpha is given, whatever is given. So this theta plus alpha is 90 degrees. So this we have done yesterday. That is electric flux. Now today, another term we will discuss, that is solid angle, and after that we will discuss this Gauss theorem. So angle and solid angle. Now what is angle? Angle is the inclination between two straight lines. If one straight line is drawn this way, other straight line is drawn this way, then whatever with the inclination, suppose one line this one, other line this one, then what will be, we will produce it by So this is the angle. Now how we measure this angle? So to measure this angle, we draw a circle, taking this point of intersection of these straight line, two straight line at center. If we draw one circle, whatever the radius may be, the radius of the circle is r, and we measure this length of this r. Suppose this is L1 and this radius is R1. If you consider another circle of radius R2, and suppose this length of arc is L2, then we will observe the ratio of this length of arc and radius is always constant. So this L1 over R1, L2 over R2 is same, and this is angle. So theta is L by R. You might have done in trigonometry. So this is length of arc over radius. If you take larger radius, naturally length of arc will be more. So the ratio of these two will always a constant if you don't change the inclination of the straight line. For a particular inclination, the ratio of these two will be constant, and that constant we call angle. Now similar concept is used in case of solid angle. So this angle is in two-dimensional one. This will be coming in two-dimensional case, whereas solid angle will come in three-dimensional. For example, suppose you are making a cone. Suppose we are taking this paper and making a cone like this. So this is like Jalmuri cone or the ice cream cone. So how we express this inclination of the surface, how the surface are inclined. So this inclination we express in terms of solid angle. Angle is two-dimensional figure. In two-dimensional, what is the inclination of the two straight line? That is angle. Whereas this inclination of the surface, how the surface is inclined from this particular center, like this here, from this one, how the lines are inclined. So how the different surfaces are inclined in three-dimensional figure, the solid figure, we express in terms of solid angle. So in case of solid angle, suppose this is a, whatever the shape may be, okay, maybe like this. This is the cone. So if we draw a sphere, here we are drawing a sphere of radius r. Whatever area, surface area is intersected by this sphere. If this is the cone and we consider a football here, So which part of the football is intersected by this cone? So this particular area. This is suppose R1, this is S1 surface. If you consider another one, radius R2, this is the surface, S2. Then it is observed the ratio of this surface area and square of the radius is same. Here length of arc and radius ratio is same. Here the ratio of this surface area S1 over R1 square equal to S2 over R2 square. Now, if we consider this type of area, whereas when we draw a circle, a sphere, the area will be something else. Suppose this is the radius R, this is the surface of the sphere. In this case, this area intersected by this sphere will not be same as this one. Then how will you find? So in this case, this is the radius vector. And the area vector of this one will be suppose here like this. If this angle is theta, in this case, what is happening? Radius vector this one, area vector is this one. When we are considering the sphere like this and this area we are considering, then radius vector and area vector are in the same direction. Whereas in this case, area vector which is to be considered is this one. But we are considering this area. What is the area of the cone? So it is not along radius vector. It is making some angle theta. Then what we have to do? We have to find the component of this area along this radius vector. So if this is the magnitude S, component along radius vector will become S cos theta. Is it clear? So we want component of the area which is perpendicular to the radius vector. So suppose this is the cone. You are given this area. But when we draw a sphere, it may come like this. So what we require is this area. We require this area, which is along the radius vector. So this is the radius vector, whereas this area which is given here as this is along this one. That is, if surface area which is given is not perpendicular to the radius vector, then we will have to find the component, or we can say the projection of this area along this one. So if this makes an angle theta, then this particular area, which is suppose S dash, this will be S cos theta. And the solid angle is suppose we give the symbol delta omega like this. Or in some book you will find like this. So if area is not given perpendicular to this radius vector or not along radius vector, then you will have to break it into components. We will have to find the angle between this area vector which is given and the radius vector. And then this will become, this delta omega will become S cos theta over R square. This is S dash over R square we require. So if area vector and radius vector are not in the same direction, then this way. In this case, radius vector and area vector are in the same direction. That is angle theta is 0. So it will be simply S over R square. Got the point? For example, again we are taking the same thing. So suppose this one. So this area we are knowing, but this is not the perpendicular to this radius. Perpendicular to radius will be, if we cut like this, then this area will be the perpendicular to that. So if this area is taken, then component of this area or projection of this area along this axis we have to find. So this general formula for this will be S cos theta over R square. Now what is the total angle at a particular point? Suppose this is the point, what will be the total angle? And if this straight line is coming this way only, other straight line is coming this way. So it is 360 degree. If we apply the same formula, that is L over R, what will come? So total angle at a point. Total length of R. So total length of R is 2 pi R over R. So it is 2 pi. That is 360 degree or 2 pi radian. Similarly, if we find total solid angle at a particular point, what will it be? So if we rotate this cone up to here, what will come? The whole sphere. So total solid angle this is total surface area, and total surface area when we will consider this will be the area of the sphere. Area of the sphere so it will become 4 pi R square over R square. So it is 4 pi steradian. Here the angle is, you can write full. So this one will become 4 pi steradian. So total angle at a point is 2 pi radian or 360 degree, whereas total solid angle at a particular point will become 4 pi steradian. So these two things we will keep in mind before studying this Gauss theorem. Or any confusion? Now Gauss theorem. Or Gauss's theorem, whatever it is. This theorem says total electric flux linked to any closed surface is 1 by epsilon naught times the algebraic sum. All the charges enclosed by so total electric flux linked to any closed surface is 1 by epsilon naught, or epsilon we can say. If vacuum is not there, then epsilon will be there, so we can write epsilon only. If air or vacuum is there, epsilon naught. For any other medium, 1 by epsilon times the algebraic sum of all the charges enclosed by the surface. And we say, particularly we write this total electric flux total. This will be 1 by epsilon times this summation is algebraic of U. Or sometimes we write like this, d phi of this is meaning is for closed surface. If we do the integration for closed surface, this will be 1 by epsilon times this type of is say for closed surface. Or we'll learn like this only, no problem. So integration so we like this only. So total electric flux linked to any surface is this one. So what does it mean? Suppose we are considering any surface like this. Here is plus 2 coulomb charge, minus 5 coulomb charge, this is placed here, this is placed here, and plus 10 coulomb charge are placed here. Then what does it mean? Due to this positive charge, what will be? Electric lines of force will come out. Due to this also it will come out, but due to this, it will go inside. So if we find the total flux linked to this one, finally, electric lines of force will come out from this one because this positive charge is dominating. So if we calculate the total electric flux, what will be according to this? 1 by epsilon naught time how much? 10 plus 2 minus 5. That is the meaning. Say 1 over epsilon or 7 over epsilon naught. That will be the total electric flux. So if this is the closed surface, plus 2 coulomb here, minus 3 coulomb here. What is the total flux link? Due to this charge, it is going out, sorry, like this. Due to this, maybe like this, So what is the, according to this theorem, what should be the total flux link to this surface? How much? Yes?
So it is not inside the closed surface only.
Yes. So what will be?
0.
0. So as no charge is present inside, we are not interested in the charge which is outside. Afterwards, we will prove that the charge when it is present outside, total flux will be 0. So here it will become 0 over epsilon naught. That is 0. So if charge is present outside, according to this theorem, if charge is present outside, total flux link should be 0. Afterwards, we will prove it also, that when the charge is present outside, total flux will be 0. So electric lines of force will come out or go inside also, but then also it will become 0. So we will prove these two things. Now, proof of this theorem. So statement you understood? Here, algebraic sum of charge means what? We have to consider the sign also, whether it is positive charge, whether it is negative charge. So total we will find, and accordingly, flux, total flux may be positive, may be negative. Yesterday already we have discussed. Positive flux means what? Total charge, net charge enclosed will be positive. If net charge enclosed is negative, naturally total flux linked will become negative. Now, proof of Gauss theorem. When you are asked state and prove Gauss theorem, we have to prove for any irregular shaped solid figure, means closed figure. In the book it is given two. One is the sphere one, that you have not to do. If you are asked state and prove Gauss theorem, that means general case we will take. of any irregular shape surface may be, closed surface may be. Till 14. Ravel and Mogal and Vinay, Pansu, Ila, Ganesh, Jimmy, Archana, Nikita, Raju, Sakshi, Reyes, Sahana, and Sukhnandan is also there. They are joining from yesterday. Where is Shivam Pandey? Mohit is not there. How you got 10 out of 10, Sukhnandan? How you manage? Sukhnandan, only 2 has got 10 out of 10. No, 3 has got 10 out of 10. One is Sukhnandan, one is Mohit, and one is Asa. What you did? No one will reveal how they have managed. What happened to you, Ila? Only 4?
Sir, my mistake, that sign convention, that mistake I've done.
Huh?
That sign one problem by mistake I've done. Plus minus.
Okay, it was the first time, so be serious.
I got 0, sir.
Now, proof of Gauss theorem. So for that, we are considering any irregular shape solid surface, means closed surface. Now, for our convenience, we are taking only one charge is present. Okay, suppose plus Q is present. As flux is a scalar quantity, it has got only 2 sides. It may be positive, it may be negative. So due to this, we will find what is the total flux. Similarly, if many other charges are there, then we will find the flux due to this second one, due to third one, and then we will find combined total only will find. Okay, suppose a charge or point charge is placed at this place. Now we may consider a particular area. Okay, suppose we are considering this one, and this is the area we are considering very small one. No? So this is the duster, charge is enclosed. So we are considering very small part of this duster, very small area. So in 3 dimensions, we can't make like that figure. So you have to just consider like a football, a small part of the football we are considering here. As the surface is irregular, charge may be present anywhere, no problem. So here, electric lines of force due to this will be in this direction. This will be the electric lines of force direction. Maybe so many are coming here. And it is a point charge, so all the lines of force starting from there only. Now, if this is at a distance, suppose this surface is ds or delta s, and the area vector will be in this direction. Suppose it is in this direction. This delta s will be vector in this direction. So it is little inclined. So electric field intensity in this direction, whereas area vector in this direction. They are not in same direction. If you consider a sphere and charge is placed at the center, then it is electric field intensity and area vector both are in same direction. That is the simplest one. But we are taking the general case. Whatever the situation may be, whether surface is of uniform shape or irregular shape, no problem. This law is valid for all. So suppose this distance is r. So if you are asked to prove that, then we will start. Let a charge Q be enclosed by an irregular shape. Okay. As shown in the diagram. Whatever the shape of surface may be. So charge is present at O. This point we are considering at P. So let us consider a small area delta S what point P should not be suitable one. Okay. Let us consider a small area delta S of the surface. Okay, about point P or around point P, whatever you may say. This language you have to see whether it is correct or not. About point it means. Okay, so what will be the electric field intensity? At electric field intensity due to plus Q charge at point P. This E will be 1 by 4 pi epsilon naught. If we are considering air or vacuum, then epsilon naught. If any other medium is there, then epsilon naught, epsilon r will also come. Okay, so we take general case suppose epsilon naught, epsilon r, q over r square, and the direction will be along OP.
Sir, epsilon r how came, sir?
Yeah, you can write K. K will be generally we are using for this whole. Sometime in the question paper, it will be given dielectric constant K is this one. Then you will have to use that one only. Otherwise, generally we use epsilon naught, epsilon r. Epsilon r or K dielectric constant is same. In place of that, we will write epsilon only. Okay, along OP. Now we are saying let this area vector delta S makes angle theta with electric field intensity. So this angle we are saying it is theta. Then electric flux linked to this surface what will be? This is E delta S cos theta. E cos theta it is. Electric flux is E A cos theta is area, and here area we have considered delta S. So this is 1 by 4 pi epsilon. In place of epsilon r, we are writing 4 pi epsilon Q over R square. So if Q is positive, this flux will be positive. If Q is negative, flux will be also negative. So this delta phi, we are writing it 1 by 4 pi epsilon Q delta S cos theta over R square. So this R square we have written here. Now what is this? Delta S cos theta over R square. What will be that?
Solid angle.
So it will be the solid angle. So whatever solid angle is made by this surface here, this is suppose delta omega we are writing. So if we consider the surface like this, whatever angle is made when we consider the cone, whatever solid angle is made by this cone here at the position of the charge, so it will be that much one. 1 by 4 pi epsilon Q delta omega, where delta omega is the or delta omega equal to delta S cos theta over R square is the solid angle made by the surface at point 2. Now we keep on adding this area so that we can find the total flux. We are finding, okay, this is the area, this area will add, this area will add, this will add, all we will add. Then what is adding? This solid angle plus this solid angle plus this solid angle plus this solid angle. So all the solid angle will be added because these all are constant. Q is same, 4 pi epsilon is same. So what is left? Only solid angle. So if we consider the total flux linked to this surface, we have to simply find the summation of this solid angle. That is total solid angle at point O. And how much it will become? 4 pi. So total flux linked to the closed surface is phi E will be equal to summation of delta pi, which is 1 by 4 pi epsilon Q summation of this solid angle sum. So this phi E will be 1 by 4 pi epsilon Q into 4 pi. Hence, total solid angle at any point is 4 pi. So this phi is 1 by epsilon naught times Q. So when we have considered only one charge, 1 by epsilon times Q. If many charges are there, then due to this Q1, Q2, Q3, whatever it is, because 1 by epsilon is same for all, only it will be the addition of the charges. So if many charges are enclosed, by the surface, then this phi will be how much? 1 by epsilon Q1 plus Q2 plus Q3 plus whatever it is. So it is 1 by epsilon naught times summation of Q. This summation we have to consider algebraic. That is sign also we have to consider. We are not considering only magnitude. We have to consider the sign also. So whether surface is regular, whether it is irregular, whatever it may be, the Gauss theorem is applicable to all. It is not only for regular surface. So it is applicable to all the surface. Only thing we have to consider is we have to consider the closed surface. The surface must be closed. Now suppose the charge is present outside, then what will happen? So suppose this is the shape, whatever the shape you consider, and here is the charge. So if we consider the electric lines of force, it's coming this way. Okay, so like that it is going. All the electric lines of force may be this way, many others are there. So what is happening here? Now suppose this part we are considering, okay, we are considering this part. What is happening? This is not intersecting the surface. So electric flux linked to these lines will be 0. Now electric flux due to these lines. What is happening here? Here this line is going inside and coming out from here. So if you consider two lines which are very close to each other, what will be due to this and due to this, electric flux will be just opposite. Here electric lines of force is going inside. Here it is coming out. So here flux link will be negative. Here flux link will be positive. As the solid angle is same, so flux will be same. And we have derived this delta phi is how much? 1 by 4 pi epsilon and delta omega. Q is also there. So in this case, this delta phi is negative, and here delta phi is positive. As in this case, what will be this area vector in this direction? Here area vector in the same direction, means angle is less than 90 degree. So flux will be positive. Here flux will be negative. So whatever flux is negative, same flux positive. So net flux will become 0. So in this case, either electric lines of force will not intersect the surface, or if it is intersecting, it will intersect twice or maybe 4 times also. Here, 1, 2, 3, 4 times. What is happening? Here, if you consider two lines which are very close to each other, maybe like this. What is happening here? Here, electric lines of force is going inside, area vector this side. Delta phi negative. Here, delta phi positive. Here again, same delta phi. Delta phi negative. But here again, it is entering into area vector this side. Here, delta phi positive. So either line will not intersect, so delta phi will be 0 for due to this line. Or if it is intersecting, then what will be? It will intersect twice or 4 times or 6 times. So naturally, what will be the net flux linked to this surface will become 0. Due to each electric lines of force, the net flux linked will be 0. Got the point? So when the charge is present outside the surface, net flux linked to the surface will be 0. So then what will be? Then total flux linked to closed surface will be 0. What about, are sleeping or what?
No, sir, we are listening.
No response?
So we are listening.
Understanding or understanding?
We are listening, sir.
Listening only, not understanding.
Yes, understanding. If we have doubt, then we are telling you.
Abhinav? He is sleeping.
Yes, sir. Yes, sir. I'm here.
Yes, sir. Response. And
Yeah.
Sukhnandan? Where is Sukhnandan? No net. What? Left or present is still?
Sir, he is present.
Huh? Present. Sleeping. Yeah, sleeping, I think. Okay. So, now we will derive Coulomb's law by using Gauss theorem. So Coulomb's law says the force of attraction or repulsion between any two charges is directly proportional to product of the two charges and inversely proportional to square of the distance. That is Coulomb's law. Now, suppose two charges are present here. This is plus Q1, and other charge is here, maybe plus Q2. We may assume minus Q2, no problem. Then we have to consider the sphere also. So here is Q1, and at a distance R, Q2 is present. So according to Gauss theorem, what will be here? Electric lines of force is in this direction. So as all the points are equidistant, all the point of this sphere we are considering. So we are considering, because when we want to apply Gauss theorem, we will have to consider a closed surface that we call Gaussian surface. That Gaussian surface may be sphere, maybe cylinder, maybe cube, whatever it is, whatever the shape may be, according to our convenience, we can change the shape. Afterwards, we will discuss what type of shape we have to consider. So when we want to apply Gauss theorem, we will have to consider a Gaussian surface. So a closed surface we are considering, that surface is spherical in shape. So a sphere, which is just this Q2 is just present on the surface of this one. That Q2 is not inside the sphere. Q2 is just outside the sphere. So how much force will be experienced by this Q2? How will you find? What is the electric field intensity produced due to Q1 into Q2? So force experienced by Q2 will be Q2 into electric field intensity produced Q2 Q1. F will be QE. So if this is the electric field, this one, then this force is how much? Q2 into E. If Q2 is positive in the direction of electric field intensity, everywhere we are taking electric field intensity same as each point of this sphere is at the same distance. Taking this Q1 as center, we have drawn a sphere. So this taking Q1, position of Q1 at center, a sphere of radius R is drawn. Therefore, the charge Q2 is present just outside the sphere. Or on the sphere, but outside, not inside. So that we say just outside the sphere. It is present on the sphere only, but on the outer surface, not on the inner surface. Then force experienced by Q2 will be this much. Now we are interested to find the value of E, and for that we will use the Gauss theorem. So, as electric field intensity is delta S and E are both on the same side, anywhere you consider small area, so delta S and E are in same direction. So as electric field intensity is uniform, magnitude only, not uniform, we will not write uniform, as magnitude of electric field intensity, magnitude of electric field intensity is same at all the points of the sphere, or sometimes we call Gaussian sphere, Gaussian surface. Or Gaussian sphere. Means in order to apply Gauss theorem, we are considering this surface. That's why the name is Gaussian surface. And direction of electric field is along the area vector. Therefore, what will be this delta phi, or the total phi, we can say this phi will be summation of delta phi, which is E delta S cos 0 summation. E is same everywhere, so only summation of delta S is left. Now, what is the summation of this delta S? This is 4 pi r square. That is the area of the sphere.
So don't draw the down part, sir.
Over.
Yes, sir.
So, what will be this? So, this phi will be E into 4 pi r square, because summation of delta S is area of the sphere. Which is 4 pi r square. Now, according to Gauss theorem, what will be? This pi is how much? 1 by epsilon naught times the charge enclosed. Therefore, what will be? This 1 by epsilon naught or epsilon times q1 is equal to E into 4 pi r square. So E we got 1 by 4 pi epsilon q1 over r square. So this you can give equation number 1, this one you can give equation number 2. So if you substitute the value of this E in equation number 1, what you will get? So this F will be 1 by 4 pi epsilon naught q1 over r square into q2.
Sir, epsilon or epsilon naught?
Yes?
Sir, epsilon or epsilon naught?
Okay, epsilon only. We have used epsilon only, not epsilon naught. So 1 by 4 pi epsilon q1 q2 over r square, and that is Coulomb's law. So this F is 1 by 4 pi epsilon, that is constant, q1 q2 over r square. This is along E, we can say. If both are positive, both are negative, then along E, that is whatever the direction E will be. So magnitude of the force is 1 by 4 pi epsilon naught q1 q2 over r square, and this is Coulomb's law. So in this way, we have derived Coulomb's law by using Gauss theorem. Over चलेगा? Now, applications of Gauss theorem to find electric field intensity in different situations. So 3, 4 are in our syllabus. So we derive one by one. One will be in case of sphere, solid sphere. Second is spherical shell. Third is line charge, that is infinitely long rod or wire when the charge due to that, and then due to this one plate, infinitely charged plate. Surface area is infinite. So if it is charged, then what will be the electric field intensity? So these are 4 cases we have to find. Okay, that we will discuss next day. Today you do something. Okay, suppose you are asked okay, suppose there is a cube. A charge is present, each side of the cube is A. A charge Q is present at the center of this cube. You are asked what is the flux linked to each surface of the cube. Find flux linked to each surface of the cube. So in this case, what will you do? As the charge is present at the center, so electric lines of force will be uniformly distributed. So due to this charge, total flux linked to all the surface, how much it will come? Total flux linked to all the surface of fluid. That will be 1 by epsilon naught or epsilon times Q. No? According to Gauss theorem, total flux linked to all the surfaces, wherever the charge may be, charge is present here, 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 anywhere. Surface is whatever the shape may be. This formula is the basic one. This is applicable to all the situations. Whatever the situation may be, only the surface should be closed. As it is a cube, so it is the closed surface. So total flux will be this much. Now, as the charge is present at the center, so what will be? Equal number of lines will cross to all the 6 surfaces. Got the point? So whatever line is crossing this surface, suppose here it is. Okay, whatever it is crossing, suppose this much crossing like this. Okay, 1, 2, 3, 4, whatever it is. Same number of lines will cross this side also. So total number of lines crossing this surface, this surface, this surface, this. All 6 surfaces will be same. So distribution of electric lines of force will be symmetric. So charge is present at the center. Flux will be distributed equally. So flux linked to each surface. Will become 1/6 of the total flux. So it is 1/6 of 1 by epsilon times q. Yes. Now another one. Suppose this is a hemisphere. Of radius r. And the charge q is present at the center of this surface. You are asked, what is the flux linked to this hemisphere? What is the flux linked to this hemisphere?
Half q epsilon naught.
Half. So what will you do here? Can we apply Gauss theorem directly here?
No, sir.
Can we apply Gauss theorem?
It is not inside
So charge is not present inside, it is present at the surface.
surface. Yes, sir.
So we can't apply Gauss theorem directly. If the charge is present anywhere here or the surface is closed, then we can apply Gauss theorem. Now what will you do? We will consider this sphere. Okay. That is half part we have assumed. Now it is closed surface. This is the sphere. What is the total flux link? The total flux link will be Q over epsilon or epsilon naught, whatever you must say. Now it is present at the center, so it is equally divided. So what will be? So if it is equally divided, then half part this side, half part this side. So flux linked to hemisphere will become so this way. If it is open surface, then we will close it by considering the symmetric shape, so that easily we can find the flux linked to that particular surface. Total flux, this much is applicable in all the cases, whatever the shape of the surface may be. But in order to find flux linked to any particular surface, you will have to make Gaussian surface of proper shape. Okay, so we will leave up to here today. Next day we shall see how to apply Gauss law to find the electric field intensity. What about?
No, sir. Thank you, sir.
Okay, thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.